Let's review what we covered previously. The change in Gibbs free energy is found from the equation delta G equals delta H minus T delta S. We see that delta G varies with temperature. As it turns out, however, delta H and delta S at any particular temperature are little different from delta H naught and delta S naught, i.e. at 25 degrees Celsius. So as long as we have access to tabulated values in order to calculate delta H naught and delta S naught for a process, we can get a good estimate of the value of delta G and thus determine spontaneity for that process at any temperature. Let's estimate the normal boiling point of ethanol. At the normal boiling point, there's an equilibrium between the liquid and gaseous phases. Here's our strategy for tackling this one. We're going to realize that, first of all, at the normal boiling point, the change in Gibbs free energy is 0. We can imagine that we have a beaker full of ethanol, and this beaker is not full of ethanol, but let's pretend, and we've covered it, and we are maintaining it at the normal boiling point. Now, we don't know what that boiling point is. That's our job to try and figure it out. But at this temperature, there is an equilibrium between liquid particles turning into the gaseous phase and gaseous particles turning back into the liquid phase. Delta G equals 0 if we maintain it at that temperature. So what we're going to do is we're going to find delta S and delta H. In other words, we're going to find delta S naught and delta H naught because delta S and delta H at any random temperature aren't much different from delta S naught and delta H naught at 25 degrees Celsius. And of course, the standard values have been tabulated. We can look those up. We can go products minus reactants and find those values, and we're just going to use those in this equation to find the normal boiling point of ethanol, which almost certainly is not 25 degrees Celsius. And then we're going to solve for the temperature in the Gibbs free energy equation. We're going to need to look up the standard entropies and the standard enthalpies of formation for the liquid and gas phase of ethanol. That's what L and G stand for. We should predict that there will be neither of these having a standard entropy of 0, and not surprisingly, the gaseous phase has more entropy, more chaos, more disorder. Similarly, since we have a compound on both sides of the equation, neither of the standard heats of formation should be 0, and not surprisingly, we need to release more energy to have a liquid than we need to have a gas. Our delta S naught is found by taking products minus reactants. And in our equation here, we have the gas as the product, and the coefficients are 1 in both cases. If we simply go 282.7 minus 160.7, that's going to give us our delta S naught. We'll do the same thing for our delta H naught. We're going to take the products, gas phase, minus the liquid phase. Now, Mr. B, how did you know in the equation up here at the top, how did you know to have the liquid on the reactant side and the gas on the product side? It doesn't matter, because when we're at equilibrium, there's an equal interchange between these. And do you see that if I had put the liquid on the product side and the gas on the reactant side, the sign of this delta S would have been negative, and the sign of this delta H would have also been negative. They're both positive, they're both negative. It doesn't make any difference, because when we take the Gibbs free energy equation and set delta G equal to 0 and then solve it for temperature, you can see that as long as delta H and delta S have the same sign, you're going to get the same answer either way. We're going to make sure that we have the proper units, typically values for standard heats of formation in the tables are given in kilojoules, so we need to be careful of that. And we get a number of about 349 Kelvin which is about 76 degrees Celsius. Taking a closer look, we found these values for delta H and delta S. I'm just recopying those from the previous slide so we don't forget. And we estimated the normal boiling point of ethanol to be 76 degrees Celsius. In actuality, it's around 78 degrees Celsius, 78 and change. So that's a pretty good estimate. Let's look at this Gibbs free energy equation again. We calculated in the upper left corner that delta H is a positive number. We also calculated that delta S was a positive number. And we have determined that at 78 degrees Celsius, we calculated 76, but 78, delta G is 0. In other words, going back to the equation in the middle of the screen, when that temperature is about 351 Kelvin, delta G is equal to 0. Now, this 78 degrees Celsius, or 351 Kelvin, I call that the tipping point temperature. In other words, on one side of that temperature, this process is spontaneous. And on the other side of that temperature, this process is not spontaneous. Let's think through this. As the temperature increases, what happens to delta G? In other words, if instead of 351 Kelvin, if this were a bigger number, like 1000 Kelvin, well, if this changes to 1000 Kelvin, then this product right here is going to become even more negative, and so delta G will become negative. Well, what does negative mean? Negative delta G means spontaneous, left to right. And we would expect that. As the temperature increases, we should expect liquid ethanol to spontaneously change into gaseous ethanol. What about as the temperature decreases? In other words, if we go below 351 Kelvin, let's pick an easy number that's less than 351 Kelvin, let's say 0 Kelvin. Well, at 0 Kelvin, or anything below 351, this positive delta H is going to be bigger than anything we have over here, so delta G will become positive, and that means that our process is not spontaneous, left to right. It would not be spontaneous to go from the liquid phase to the gaseous phase. In fact, wouldn't it be spontaneous to go from the gaseous phase to the liquid phase?